In this video, we'll talk about multi-body problems where several different masses will be either connected by strings or in contact with each other as they're being pushed around or pulled around. In this case, we have three masses of 1 kilogram, 2 kilograms, 3 kilogram being pulled by rope 1, rope 2, and rope 3. And the overall result is that the entire thing moves with 3 meters per second acceleration. In this case, rather than do a traditional free body diagram on each of the three, which you actually can do and you'll get the right answer, we'll show you a trick to solve these problems quicker and simpler. The trick is to look at a free body diagram and consider the mass 1, mass 2, and mass 3 together. So here's a mass that's 6 kilogram, and what are the forces on that? Well, there's T3, there's a weight, an FG, and a normal force. Okay. In this case, because the problem is frictionless, it doesn't matter what's going on vertically. We don't care about the weight and the normal force. We can just focus on the acceleration caused by this force acting on this mass. So we're looking at T3 essentially pulling all three masses together. When we do that and we use Newton's second law, then T3 equals 6 kilograms, that's the mass, and the acceleration is 3 meters per second squared, and so that equals 18 newtons. All right, so we really didn't have to worry about what's going on inside between the multiple masses. We just looked at them as if they were all together. So that gave me T3. What about T2? I can look at T2 and say, all right, T2 pulls the 1 kilogram mass and the 2 kilogram mass. So I can say that's 3 kilograms, and it gets pulled by T2. Yeah, there's a normal force and a other force down for weight, but I really don't care. T2 equals 3 kilograms times 3 meters per second squared, which equals 9 newtons. So notice that this force is much, much less than the other one because you're pulling much less mass. Lastly, I can look at the very far left. I have a 1 kilogram mass being pulled with T1. I have a normal force and a weight again, but I really don't care about those. So here T1 equals 1 kilogram times 3 meters per second squared. That equals 3 newtons. So in this case, we have 3 newtons, 9 newtons, and 18 newtons. It's very important to get the order correct, so note that the largest force pulls all three masses. The middle force pulls 2 masses, and the smallest force pulls only the 1 mass. We'll look at another example. In this case, we're looking at 3 boxes, 1, 2, and 3 kilograms, and an overall force of 24 newtons pushing the rightmost box. That will then accelerate the entire stack of boxes, and box we'll call F2 the force on box 2, and F1 the force on box 1. So the question is, what is my acceleration? And then if I find that, then what is F2 and what is F1? So let's take a free body diagram approach like we do with everything else. And I'm going to combine all three masses, so that's 6 kilograms, and it's being pushed with 24 newtons of force. So the force is 24 newtons. That equals 6 kilograms times an acceleration. So A equals 24 divided by 6, or 4 meters per second squared. So all three boxes are moving at that acceleration. Now, if that's true, let's look and see if we can identify what the size of F1 and F2 are. All three boxes move at that acceleration. So now I'll look at the force 2, and in this case I have a mass that force is pushing 3 kilograms of mass, and I have some force called F2, and I know that results in 4 meters per second squared of acceleration. So F2 equals 3 kilograms times 4 meters per second squared acceleration, and that's 12 newtons. So over here I have 12 newtons. Lastly, I have the leftmost mass, which is 1 kilogram. I have a push called F1. So again, F1 equals 1 kilogram times 4 meters per second squared. And that equals 4 newtons. All right, so does this make sense? The biggest force, 24 newtons, pushes on all three masses. The middle force, 12 newton, pushes on 2 masses, and the smallest force pushes just on 1 mass. So this is a very powerful technique for solving these kinds of problems pretty quickly, and I think in a very commonsensical way. Hope that helped.